In order to guarantee full understanding of this course, you should have completed previous universal molding modules: MU1 Introduction, MU2 Fundamentals, MU3 Molding with Graphs, and MU4 Material Morphology. Your objective should be to identify what your process needs and to attend to those needs with well-thought-out solutions. Because of this, before molding or making any type of adjustments to your injection molding machine, you should make certain initial calculations. These initial adjustments are known as molding from the desk. Remember that you are dealing with expensive equipment and should not rush your work. In this course, we will discuss fundamentals of clamping force, projected area, thin wall calculation, forces resulting from side action mechanisms, press spacing, press opening, ejector or knockout patterns, fundamentals of clamping force. There's a difference between the closing force that the press is capable of and the force that is required to keep the mold closed. The melt that flows into the mold cavities enters at high pressure, and the press should create the force necessary to contain this pressure. Force is normally measured in U.S. tons, 2,000 pounds of force, or metric tons, 1,000 kilograms of force. 1 metric ton is equal to 1.10 U.S. tons. A U.S. ton is equal to 8.9 kilonewtons. So a metric ton is equal to 9.81 kilonewtons. We can determine the clamping force with the following equation. Force is equal to pressure times area. Pressure. Melt pressure varies depending on the type of material. For example, each material has a pressure factor measured in units of force divided by area. Some of these pressure factors are polypropylene, whose pressure factor is 1.5 to 3.5 U.S. tons per square inch, or 2.1 to 4.8 kilonewtons per square centimeter. Nylon 66, whose pressure factor is 3.0 to 5.0 U.S. tons per square inch, or 4.1 to 6.9 kilonewtons per square centimeter. And rigid PVC, whose pressure factor is 2.0 to 3.0 U.S. tons per square inch, or 2.8 to 4.1 kilonewtons per square centimeter.
Does the pressure factor vary depending upon the resin's manufacturer?
Yes. The pressure factor should be obtained from the resin manufacturer. The table is a reference only. Verify the specifics of your resin with its manufacturer. Projected area. The projected area is the plane or surface which is seen in the mold's partition, known as the parting line. For example, a sphere's parting line would be seen as a circular plane. The area would be equal to diameter squared times pi divided by 4. Another example. A cube's plane would be square or rectangular. The area would be the width times the height. A third example. Consider a form where the largest diameter is the parting line. The area would equal the largest diameter squared times pi divided by 4.
So we don't consider the depth of the cavity?
Not while determining the projected area. It's simple. If the projected area increases, then the required clamping force will also increase. Various aspects must be taken into consideration when determining clamping force: the material and its characteristics, understanding the way the melt flow fills the cavities, the projected area of all the cavities, the projected area of the runner, type of mold, 3 plates or stacked mold, springs that act against the clamping force, sliders that add additional load to the clamping force, that the clamping force the press is capable of should always be more than the clamping force required by the mold.
Then the clamping force should be adjusted to its maximum?
No. With time, excessive force could cause damage to the cavities, especially to the vents. Remember that the gases inside the cavities and the runner are released through small openings during fill. These small spaces, called vents, allow those gases to escape. If the clamping force is excessive, the vents could get choked.
What happens when the vents get choked?
It will make it difficult for the gases to escape. Remember that part of these gases come from the melt. and at high pressure these gases can actually combust, an action called dieseling. The molded parts will show burn marks at the end of the fill, close to the choked vents. Let's look at an example, courtesy of Peter Paul Electric. A nylon spool is manufactured using a 12-cavity mold. The gate from the cavity is shown in the superior view. In this example, the clamping force would be the result of projected area of all the cavities, projected area of the runner, and slider action. The projected area corresponds to 12 circles with a hole in each center, plus the area of the runner. The projected area of a circle with a hole in the center is calculated by subtracting the area of the minor or interior diameter from the major or exterior diameter's area. Area of the parts equals the diameter of the exterior squared minus the diameter of the interior squared divided by 4 times pi. In this example, this would equal 2.94 square centimeters or 0.46 square inches. The projected area of the runner can be simplified by approximating it using rectangles and circles. Think of half of the runner as being composed of 2 rectangles with an area of height times width, and a circle with an area of diameter squared times pi divided by 4. The area of the runner would be the sum of 4 rectangles and 1 circle. The projected area of the runner would equal 35.29 square centimeters or 5.47 square inches.
Why don't we consider the area where the runner branches to the gates?
It could be considered, though for this approximation we assume that amount is negligible.
What should we do when we have irregular geometry, which cannot be calculated using conventional means?
Graph paper is a good option. Trace the component on the paper and count the squares inside the drawing, considering half and third squares if possible. Then multiply by the area of each square. Another alternative would be using the area function of a CAD program. For this, you would need a digital drawing of the component. Finally, add all of the areas. The total area would equal the area of the runner plus 12 times the spool area. In this case, it would equal 71 centimeters squared or 11 inches squared. Resin manufacturer Acme states that the clamping force factor for nylon is 4.1 to 6.9 kilonewtons per square centimeter, or 3 to 5 U.S. tons per square inch. Using the minimum force factor of 4.1 kilonewtons per square centimeter, or 3 U.S. tons per square inch, you would need a clamping force of 291 kilonewtons, or 33 U.S. tons. Using the maximum force factor of 6.9 kilonewtons per square centimeter, or 5 U.S. tons per square inch, you would need a clamping force of 490 kilonewtons, or 55 U.S. tons.
What pressure factor should we use? 4.1 kilonewtons per centimeter squared, or 6.9.
The pressure factor would depend upon how difficult it is to fill the mold. For example, if we consider that thin walls would require more fill pressure than thick walls, a large fill travel would require more pressure than a short fill travel, the pressure factor would depend upon a thin wall calculation, a value that takes into consideration the fill distance and the thickness of the spaces. Thin wall calculation. A thin wall calculation is a factor representing fill difficulty. This factor takes into consideration the distance that the melt has to travel and how narrow the passages are. This factor is represented by the following equation. Thin wall calculation equals farthest flow path divided by thinnest wall on the path. Thin wall calculation is a value that represents the fill difficulty. This difficulty increases when the value increases. The farthest flow path is the path of the flow from the gate to the farthest fill point. The thinnest wall on the path is the thickness of the thinnest wall on the farthest flow path. Let's look at an example. The isometric L form shows superior and front views. The farthest flow path can be approximated by finding the sum of x and y. The thinnest wall on the path is W. So the thin wall calculation is equal to x plus y divided by W. Let's continue with the spool's thin wall calculation. The farthest flow path, or the path from the gate to the selected farthest point, is shown by the blue line. The farthest flow path would then be calculated by x plus y plus z.
If the spool is a cylindrical part with a hole in the middle, Why is the trajectory linearly represented?
The melt will flow through the path of least resistance, and the path of y is probably diagonal and around the circumference of the spool. If you have a numerical analysis program, excellent. Use it. Also, remember that we are molding from the desk. Don't try to complicate your life with calculations that won't necessarily give the best results. So the farthest flow path is equal to x plus y plus z, or in this case, 50 millimeters or 1.97 inches. Now let's look at the thinnest wall from the chosen path in the drawing below, where we find that the thinnest wall is the center wall of the spool, and we call this thickness T. In this case, T is equal to 1.22 millimeters, or 48/1000ths of an inch.
Can I choose a thickness outside of the chosen path?
No. Remember, there's a relationship between the flow path and the thickness of the walls. If you want to, you can make various thin wall calculations using distinct paths. However, the thinnest wall should be along the chosen flow path.
If we make a variety of thin wall calculations, which of the determined values should we use?
Choose the largest, since it represents the worst condition. The thin wall calculation, or TW, of the spool is equal to 50 millimeters divided by 1.22 millimeters, or 41. Thin wall criteria. If the value of TW is 100 or less, use the smallest pressure factor. Force is equal to projected area times smallest pressure factor. If the value of TW is between 100 and 200, interpolate between the pressure factors. Force is equal to projected area times interpolated pressure factor. If the value of TW is 200 or more, use the largest pressure factor. Force is equal to projected area times largest pressure factor. Use a lineal interpolation to obtain the interpolated pressure factor. With the spool example, we had a pressure factor for nylon of 4.1 to 6.9 kilonewtons per square centimeter, or 3 to 5 U.S. tons per square inch, and an obtained thin wall value of 41. According to the indicated criteria, if less than 100, we use the minimum pressure factor, 4.1 kilonewtons per square centimeter, or 3 U.S. tons per square inch. This means that the normal clamping force, due to the projected area and the pressure factor, is normal force equals pressure times area. In this case, this equals 291 kilonewtons, or 33 U.S. tons. Forces resulting from side action mechanisms. One reason for selecting a spool as an example is because the projected area in the mold's partition is more than a simple force calculation. The clamping force can be affected by forces as a result of mechanisms that act laterally. These mechanisms are part of the mold cavities, and they stay in position while the mold is closed. After the mold opens, those mechanisms move, freeing the molded parts. These lateral forces influence the clamping force, since the press is what holds them in place. The simplified animation below illustrates how the cavity separates in order to free the molded part. Each cavity separates in the middle by means of 2 sliders that will experiment a force as the result of the melt pressure. This force will be the result of the melt pressure, 4.1 kilonewtons per square centimeter, multiplied by the projected area in the cavity partition. With the area in the partition, we can assume that the extremities have a negligible area, so our calculations will be based on the area of a rectangle. In this case, the projected area will equal 3.54 square centimeters, or 0.55 square inches. So the lateral force per slider equals the lateral projected area times the pressure factor, which equals 14.5 kilonewtons per slider, or 1.65 U.S. tons per slider. According to this number, each half of the cavity will have a force of 14.5 kilonewtons, or 1.56 U.S. tons, trying to separate it. Taking into consideration that there are 12 cavities and that each cavity is maintained closed by means of wedges, the lateral force will be determined by the following equation. Lateral force equals force per slider times 2 sliders times 12 cavities, which equals 348 kilonewtons, or 40 U.S. tons. This number, 348 kilonewtons, is the total force that the melt will exert laterally against the wedges. These wedges are manufactured with an angle, in this case 15 degrees, and only a fraction of this lateral force will be seen in the direction of the closing press. This resulting force in the direction of the press will be found by multiplying the lateral force by the tangent of the angle of the wedge. Lateral force action equals lateral force times the tangent of 15 degrees, which equals 94 kilonewtons or 10.8 US tons. The total clamping force required for the mold will be the sum of the force resulting from the melt in the partition of the mold and from the lateral force action of the cavities. Final force equals normal force plus lateral force action, which equals 385 kilonewtons or 43.8 US tons.
Do I have to make these calculations if the mold manufacturer has already recommended a clamping force?
Yes, they should be corroborated. Molding from the desk is a practice that we should all do before attempting to adjust the press.
Wouldn't it be easier to adjust the clamping force of the press to its maximum?
It would be the easiest, but not correct. Excessive force would eventually damage the mold by, for example, deforming the small vents in the cavities. If the vents block the escape of gas, then air, mixed with vapor from the same melt inside the cavities, could cause the dieseling effect. Remember that the dieseling effect is an explosion due to a combustion of gas at high pressures. The next time you find burn marks on the molded parts near the vents, verify the clamping force before trying to repair the mold. Other factors that must be taken into consideration are the springs. If your mold uses springs that are compressed when the mold is closed, add the force of each spring. You can get the force factor of the springs from their manufacturers.
Why does the mold need springs?
They are basically used to keep some components separated while the mold is open. One example of this would be helping to open stripper plates. 3-plate mold. This type of mold has two distinct mold plates for the parts and for the runner. The mold separates into two partitions. In one partition, the parts are molded, and the runner forms in the other.
What would a mold like this be used for?
It's common to find this type of design used when the molded part needs to be injected in the center, like round parts. Calculating the clamping force of a 3-plate mold must be done 2 times, in the partition where the parts are molded and in the part that creates the runner. Later you will choose the larger of the two. It is common for the force of the molded parts to be more than the force of the runner, but this is not true in 100% of the cases. Do all the calculations and select the largest. Stack mold. A stack mold has the same number of cavities in each side of the mold. Since the same number of identical parts come from both sides of the mold, the clamping force of each side will be equal. Because of this, we only have to take the clamping force of one side into consideration.
Why consider only one half instead of using both?
You only need to consider one side. This is what makes the stack design attractive. It produces twice the parts without needing twice the clamping force. Look at the illustration, which shows force vectors. Forces of equal magnitude, in opposite directions, will try to open each face of the mold. The vectors in the center will cancel each other, resulting in the equivalent force of only one side. Besides clamping force, you should verify that the mold fits properly in the press and that the ejector pattern of the press coincides with the pattern of the mold. Press spacing. With tie bars. If the press has tie bars, verify that the mold fits in between them. It may fit inside the 4 bars, vertically between the bars, or horizontally between the bars. Tie barless. Tie barless presses provide better flexibility for positioning the molds. Even so, you must verify the available space. Press opening. Verify that the minimum opening of the press is enough so that the mold can be pressed closed. Also verify that the mold opens enough so that the parts can be demolded. Ejector or knockout patterns. Verify that your press has the ejector pattern that is required for your mold. Though the majority of these verifications seem simple and obvious, do your work and verify it. Those who have been present when a mold was transferred to the wrong press understand this advice, and those who have never had this happen to them need to avoid it.
Let's review.
Important. Before molding or making any type of adjustments to your press, you must make initial calculations. Remember that this is work that cannot be rushed. Make your initial calculations at your desk.